In 1950, they ran an F1 engine on castor oil, methanol, and basically moonshine. It got 1.5 miles per gallon and shook the driver half to death. In 2026, an F1 engine is so advanced, NASA engineers study it. Part 1. The Birth of the Beast, 1947 to 1953. To understand where we are, we have to go back to 1950. The world was still rebuilding after World War II, and the FIA, the guys who run the show, decided they needed a Formula One. The rules back then were basically a choose-your-own-adventure book. You had two choices: a massive 4.5-liter engine that breathed regular air, naturally aspirated, a tiny 1.5-liter engine with a supercharger bolted onto it, the straight 8, the Alfa Romeo Alfetta. The first king of F1 was the Alfa Romeo 158. It used a straight 8 layout. Now picture this: 8 cylinders in one long straight line. The good: it was incredibly smooth. Because the cylinders are lined up, the vibrations naturally cancel each other out. It was a masterpiece of balance. The bad: it was long, I mean really long. It made the car feel like a boat. The fun fact: to get 350 to 425 horsepower out of this 1.5-liter engine, which is insane for the 50s, they ran it on a witch's brew of fuel. We're talking methanol, benzol, and castor oil. It drank fuel so fast it only got about 1.5 miles per gallon. The cars had to have these massive fuel tanks, and as the fuel burned off, the car would lose hundreds of pounds. Imagine trying to drive a car that gets lighter and handles differently every single lap. The 4.5-liter V12, the Ferrari counterattack. While Alfa was busy supercharging their engines into oblivion, Enzo Ferrari had a different idea. He hired a guy named Aurelio Lampredi to build a 4.5-liter V12. Think about the logic here. Instead of a tiny engine working really hard with a supercharger, why not build a huge engine that breathes easily? The V12 had 12 cylinders in 2 banks of 6. This layout allowed for smaller pistons, which meant they could rev higher than a big 4-cylinder or 6-cylinder. It was way more fuel efficient than the Alfas. In 1951, Ferrari finally beat the invincible Alfas, proving that displacement and efficiency could beat raw, supercharged boost. The BRM V16, the greatest sounding failure. We can't talk about this era without mentioning the BRM V16. This thing is the stuff of legends and nightmares. British Racing Motors, BRM, wanted to build a national hero. They built a 1.5-liter engine, but they gave it 16 cylinders. The pistons were the size of shot glasses. Seriously, they were tiny. To make it go, they used a massive centrifugal supercharger designed by Rolls-Royce, basically a piece of a Spitfire engine. It produced over 600 horsepower at 12,000 revolutions per minute in 1950. But here's the thing: it was a disaster. The boost didn't arrive smoothly. It arrived like a kick in the teeth. The driver would step on the gas, nothing would happen for a second, and then suddenly, boom! 600 horsepower hits the rear wheels and they just spin. It blew head gaskets constantly and was almost impossible to keep cool. It's often called the greatest sounding engine ever, but it never won a major championship race. It was too complex for its own good. Part 2. The Silver Arrow Revolution, 1954 to 1960. In 1954, the FIA got worried. The cars were getting too fast and too dangerous, so they changed the rules. Engines were now limited to 2.5 liters naturally aspirated. This is when Mercedes-Benz decided to come back and show everyone how it was done. The Mercedes M196, the high-tech straight 8. Mercedes brought the W196, powered by an inline-8 engine. But this wasn't your grandpa's straight 8. They used 2 pieces of tech that were basically science fiction at the time. First, direct fuel injection. Most cars in the 50s used carburetors, which are basically controlled leaks. They're not very precise. Mercedes used a system adapted from the Messerschmitt fighter planes. It sprayed fuel directly into the combustion chamber with perfect timing. This gave them way more power and better fuel economy. Second, desmodromic valves. This is the cool one. In a normal engine, a cam pushes the valve open and a spring pulls it shut. But at high RPMs, the spring can't snap back fast enough. We call this valve float. Mercedes got rid of the springs. They used a mechanical arm to pull the valve shut. No springs, no float, no problem. It meant they could rev higher and more reliably than anyone else. Fun fact: to keep the car's profile low for better aerodynamics, They actually laid the engine on its side at a 53-degree angle. It worked so well that Juan Manuel Fangio used it to dominate the sport. The Maserati 250F, the inline-six standard. While Mercedes was using fighter plane tech, Maserati was perfecting the inline-six. Their 250F is considered one of the most beautiful and pure F1 cars ever. It wasn't as high-tech as the Mercedes, but it was simple and reliable. It produced about 240 to 270 horsepower and was so well-balanced that drivers loved it. It was the gold standard for privateers, teams that didn't have the massive budget of a factory like Mercedes or Ferrari. Part 3. The water pump era, 1961 to 1965. By 1961, the rules changed again. To slow the cars down, displacement was dropped to 1.5 liters, but naturally aspirated. This was a huge drop. Imagine taking the engine out of your car and replacing it with something the size of a lawnmower engine, the Coventry Climax V8. This era was owned by a company called Coventry Climax. And get this, they actually started out building engines for portable fire pumps. I'm not kidding. Their engines were designed to be light and reliable so firemen could carry them around. But F1 builders like Colin Chapman, the genius behind Lotus, realized these water pump engines were perfect for racing. The FWMV V8 became the heart of the British racing revolution. It was tiny, it was light, and it was efficient. It helped Jim Clark become a legend. It just goes to show, you don't always need $1 million lab. Sometimes you just need a really good pump. The Porsche 804, the air-cooled flat 8. Porsche decided to try their hand at F1 during this time, and they brought a flat 8. Instead of the cylinders being in a V, they were laid out flat like an open book. This keeps the center of gravity really low, which helps the car corner like it's on rails. But Porsche did something weird. They made it air-cooled. Instead of a radiator with water, it had a huge horizontal fan on top of the engine to blow air over the cylinders. It was powerful, but it was a nightmare to keep cool during a long, hot Grand Prix. They won one race with it, but eventually they realized that for F1, you really need water cooling. The Climax Flat 16, the great what if. At the very end of this era, Coventry Climax tried to build a Flat 16 cylinders in 1.5 liters. The idea was that more cylinders mean smaller pistons, which means higher RPMs. They wanted this thing to rev up to 12,000 plus RPMs, but it had a major flaw, a weird vibration at low RPMs that they just couldn't fix. On its first day on the test bench, it literally broke while warming up. By the time they almost had it sorted, the rules changed again, and the project was scrapped. It's one of the great missing links of F1 history. Part 4. The 3.0-liter Giants, 1966 to 1985. 1966 was the year F1 grew up. The displacement doubled to 3.0 liters. This was the return to power era. The BRM H16, the engine sandwich. BRM decided to get crazy again. They took two of their successful 1.5-liter flat 8 engines and stacked them on top of each other. One on top, one on bottom, geared together at the crankshaft. It was called an H16. It was a mechanical nightmare. It had 2 crankshafts, 8 camshafts, and 64 valves. It was so heavy, it took 4 guys just to lift it. It vibrated so much that it would shake the car to pieces. Jim Clark actually won a race with it in 1966, but he famously hated it. He said he only won because every other car on the grid broke down first. It's a perfect example of why more isn't always better. The Ford Cosworth DFV, the engine that changed everything. In 1967, a tiny company called Cosworth, with funding from Ford, built the DFV V8. DFV stands for double 4 valve. This is arguably the most important engine in history. Why? Because of how it was built. Before the DFV, you built a frame, the chassis, and dropped the engine into it. The DFV was designed as a fully stressed member. This means the engine was the back half of the car. You bolted the cockpit to the front of the engine and the suspension to the back. This made the car lighter, stiffer, and much easier to build. The DFV was so good and so cheap that almost any team could buy one and be competitive. It won 155 races over 15 years. If you've ever wondered why F1 has so many teams today, it's because the DFV made it possible for small shops to compete with giants like Ferrari. Ferrari's Flat 12, the aerodynamic wall. Ferrari didn't like the V8 dominance, so they built a Flat 12. It was incredibly powerful and had a very low center of gravity. It helped Niki Lauda win championships. But it had a hidden weakness. It was wide. In the late 70s, F1 discovered ground effect, using the underside of the car like an upside-down wing to suck it to the ground. To do that, you needed wide tunnels under the car. Ferrari's flat 12 was so wide that it blocked those tunnels. Ferrari had to abandon the 12-cylinder and move to a narrower V6 turbo just to keep up with the aerodynamics. It was a classic case of the engine losing out to the wind tunnel. Part 5. The First Turbo Era, 1977 to 1988. Okay, now we're getting into the era of raw, unadulterated madness. The turbos. The Renault V6, the yellow teapot. Renault showed up in 1977 with a tiny 1.5-liter V6 and a turbocharger. At first, everyone laughed. The car was unreliable and constantly blew up in a cloud of white smoke. They nicknamed it the yellow teapot. But Renault was onto something. A turbo uses waste exhaust gas to spin a turbine, which pumps more air into the engine. More air means more fuel, which means a bigger explosion and more power. By 1979, the teapot started winning, and the laughter stopped. Suddenly, everyone needed a turbo. The BMW M1213, the 1400 HP Grenade. This is my favorite F1 story. BMW built an inline-4 turbo, but they didn't use fancy new blocks. Legend has it, they used old cast-iron engine blocks from high-mileage road cars, some with over 100,000 kilometers on them. The lead engineer, Paul Roche, believed that if a block hadn't cracked after years on the street, the metal was seasoned and ready for the stress of racing. They even used to leave the blocks outside in the rain, and supposedly some mechanics added their own fluids to the blocks to help the seasoning process. In qualifying, they would crank the boost up to over 5 bar. That's about 80 psi. For context, your car at home probably runs at 10 or 15 psi. This tiny 1.5-liter engine was putting out an estimated 1,400 horsepower. BMW's own dyno couldn't even measure it. The needle just hit the stop at 1,280. These were called grenade engines. They were designed to last for exactly 2 laps, one to warm up and one to get pole position. After that, they were literal scrap metal. The turbo lag was so bad that drivers had to floor the gas in the middle of the corner, just so the power would show up by the time they reached the straight. It took massive guts to drive these things. Part 6. The Return to Aspiration and Exotic Dead Ends, 1989 to 1994. By 1989, the FIA said, "Enough is enough. The turbos were too fast and too dangerous." They banned them and said, "Go back to naturally aspirated engines, 3.5 liters, and we don't care how many cylinders you use, up to 12. This led to a beautiful, brief moment of mechanical diversity. You had V8s, V10s, and V12s all on the track at the same time. The Life W12, the architecture of failure. If the BMW was the peak of engineering, the Life W12 was the valley. A tiny Italian team called Life Racing Engines showed up with a W12 design. Now, when you hear W12, you probably think of a modern Bentley, but this was different. It was effectively a V8 with a third bank of cylinders standing straight up in the middle. It was called a broad arrow design. It was a total catastrophe. It produced maybe 375 to 480 horsepower. Meanwhile, the Honda V10s were making over 700. In one race at Imola, the Life car was so slow it took 7 minutes and 16 seconds to do a single lap. To put that in perspective, a modern safety car could lap it. The team was so poor they didn't even have a tire pressure gauge. They had to borrow one from another team. They never made it past pre-qualifying. The Subaru Flat 12, the heavyweight. Subaru also tried their hand at F1 with a Flat 12. It had that signature Subaru Boxer layout, and on paper it looked good. Low center of gravity, lots of cylinders. But it was a pig. It weighed nearly 100 kilograms more than the Cosworth V8 and produced 100 less horsepower. It was so wide it ruined the car's aerodynamics. Subaru lasted about half a season before they realized F1 wasn't for them and went back to rallying, which turned out to be a much better idea. Part 7. The V10 Scream and the 2.4L V8s, 1995-2013. By the mid-90s, everyone realized that the V10 was the sweet spot. It had more power than a V8, but was lighter and used less fuel than a V12. This is the era that most fans get misty-eyed about. The science of the Scream. These engines were hitting nearly 20,000 revolutions per minute. Think about that. Your car on the highway is probably sitting at 2,500 revolutions per minute. At 20,000 revolutions per minute, the pistons are moving up and down 333 times every second. Because there are 10 cylinders, you're getting a firing event every 72 degrees of crankshaft rotation. That's over 1,500 explosions every second. Your ear doesn't hear individual bangs anymore. It hears a high-pitched, visceral shriek. Technically, V10s are not naturally balanced. They have what engineers call rocking couples, a fancy way of saying they want to wobble from end to end. Teams had to use heavy balance shafts and precise bank angles, usually 72 or 90 degrees, just to keep the engine from vibrating the car into a pile of bolts. The 2.4-liter V8s and Curves. In 2006, the FIA shrunk the engines again to 2.4-liter V8s to save money and slow things down. These were basically sawn-off versions of the V10s. They were still loud and incredibly fast, but this is when we saw the first hint of the hybrid future. KERS, Kinetic Energy Recovery System. Basically, a little electric motor on the crankshaft that would catch energy when the driver braked, store it in a battery, and give them a 160 horsepower boost for a few seconds a lap. It was the beginning of the end for pure internal combustion. Part 8, the modern power unit, 2014 to present. In 2014, F1 made the biggest technical jump in its history. We moved to the 1.6-liter V6 turbo hybrid. And notice, we don't call them engines anymore. We call them power units. Why? Because the gas engine is only about 70% of the story. A modern power unit has four main pieces: the ICE, internal combustion engine, a tiny V6 that makes about 700 horsepower, the turbocharger, a snail that forces air into the engine, the MGUK, kinetic. This motor is connected to the crankshaft. When the driver brakes, it acts as a generator, slowing the car down and charging the battery. When they floor it, it acts as a motor, adding an extra 160 horsepower to the wheels. The MGUH, heat. This is the real wizardry. It's an electric motor sitting on the shaft of the turbocharger. It catches the hot exhaust gases and turns them into electricity. But it also does something cool. It works as an anti-lag device. When the driver is off the gas, the battery spins the turbo up electrically so that the instant they touch the pedal, the boost is already there. No more waiting for the snail to wake up. Thermal efficiency, the mind-blowing stat. Here's the thing that will blow your mind: 50%. Most road car engines are only about 20% to 30% thermally efficient. That means 70 to 80% of the energy in your gas is just wasted as heat and noise. Through this crazy hybrid tech, Mercedes and Ferrari have pushed F1 engines past 50% efficiency. These are the most efficient internal combustion systems on the planet, period. To put that in perspective, in a normal car, the heat screaming out of the exhaust is just lost to the atmosphere. In an F1 car, the MGUH turns that waste into pure speed. Part 9, the 2026 reboot, the future. So, what happens next? In 2026, the sport is undergoing a massive reboot. We're moving away from the era of pure complexity and toward a new kind of power. The biggest change? We're saying goodbye to the MGUH, the heat recovery wizardry that was just too expensive and complicated for its own good. By ditching it, F1 has finally made the sport attractive enough for giants like Audi and Ford to jump into the ring. But don't think for a second that these cars are getting slower. To make up for that lost heat energy, the electric side of the car is getting a massive level up. The MGUK is nearly tripling its output, jumping from 160 horsepower to a staggering 470 horsepower. The goal is a perfect 50-50 split. Half the power comes from the V6 engine, which will be running on 100% sustainable fuel, and the other half comes straight from the battery. This turns the race into a high-speed game of strategic chess. Drivers will have to be master energy managers, deciding exactly when to burn their juice for an overtake and when to save it to defend their position. It's a whole new world of tactical racing, and it's going to be wild to watch. The soul of the machine. So, looking back over 70 years, it's easy to get nostalgic. Next time you see a car fly past, listen to it. Whether it's a shriek, a whistle, or a hum, you're hearing 7 decades of geniuses trying to beat each other. If you enjoyed this deep dive, do me a huge favor. Hit that like button and let me know in the comments. If you were an F1 engineer and there were no rules, what engine layout would you build? I'm still waiting for someone to try a V24, but that might just be me. Thanks for hanging out in the garage today. I'll see you in the next one.